Okay, in this video, what we're going to do is focus on what are called single replacement reactions, and these usually involve a single non-ionized metal, so a neutral metal that undergoes a reaction with an ionic compound that contains another metal which has lost electrons, so it has a positive charge on it, and there's an exchange that takes place between the two metals. And the metal that is not ionized changes places with the metal that is ionized, and in the process of the exchange, the unionized metal loses electrons, and the metal that was initially in the ionic compound gains electrons. So these are usually oxidation reactions. All right, and the first example that we're going to look at is the reaction of iron 3 chloride. So iron 3 chloride, which is in an aqueous solution, plus zinc metal to form zinc chloride, which is aqueous, and iron metal. Now, like the past videos in this particular playlist where we're looking at specific classes of reactions, we need to balance this equation, and we can see here that we're going to need a, it's a good guess that there's going to be a 2 here, which means there's going to need to be a 2 in front of the iron here. And because 2 times 3 chlorines or chlorides is 6, we're going to need a 3 here. And that means that we're going to need a 3 in front of the zinc. All right, now coming back to the definition, you can see that in this formula, the iron 3 chloride, this is an aqueous solution, and the rule is that if you have an ionic compound and it is dissolved in water, which the AQ here, that's what that means. That means this compound is dissolved in water, then this compound must be ionized, and it is undergoing a reaction with zinc metal. So if we were to actually write what we call the net ionic equation for this, we would write 2 Fe plus 3s plus 6 Cl minuses plus 3 zincs, no charge, all right, to produce 3 zinc plus 2s plus 6 Cl minuses plus 2 Fe's that uncharged because it's the metal. Now, if you look closely at what we've got here, we see the Cl minuses actually appear on both sides of my arrow, and when we write a net ionic equation, what we want to do is cancel out the things that appear on both sides of the equation, and so that means that the Cl minuses are going to cancel out, and we call these spectator ions. Spectator ions, the Cl minuses. And that leaves us with what we call our net ionic equation. All right, now you cannot, sometimes students get confused, you cannot cancel the zinc on this side with the zinc plus 2s on this side because these guys are different. This is not ionized. This is ionized. Chemical reactions occurred. Now, coming back to the definition of single replacement, you see what's happened here if you look at the reactants. All right, and compare them, the iron went from being ionized to iron which is not ionized. All right, so the only way that could happen is if this thing gained electrons. And the zinc went from being not ionized to ionized. Now in the process, the iron and the zinc, well, let me put it this way: the zinc changed places with the iron. All right, and when you compare how the two changed places, there was only a single replacement, because this compound, this chloride, is on two sides of the equation. The main difference being is that the two chlorides differ only by the type of cation that's in the equation. All right, now I think we have time for one more example. So in this one, we're going to compare reacting magnesium with copper 2 sulfate. So again, what's unique about single replacements is usually they share a similar pattern, where you're reacting a metal with an aqueous solution that contains another metal that's actually ionized. And in this case, we're going to form magnesium sulfate, which is aqueous, and we're going to form copper metal. Okay, now in terms of balancing, this equation's already balanced. And what I want to point out again is you've got an ionic compound. Okay, you have an ionic compound that's dissolved in water, that's being combined with a metal that's not ionized, and one of the products is going to be yet another solution of ionized metal, and with the production of a new metal, all right, being the copper. So we can write the net ionic equation for this, and we start by separating out the ions that are involved in the solutions. So we write out the entire equation, and actually what we're writing at the moment is called the complete ionic. And all we're doing is separating the ions that are actually in solution from the things that are actually not dissolved. All right, and then we're going to cancel the spectator ions. All right, which happens to be the sulfate in this case. And so we write our new equation. It's going to be our magnesium plus our copper ion to produce magnesium ion and copper metal. All right, single replacement. So you can see what's happened is that this basically changes place with the copper, and we end up producing a new ionic compound and a new metal in the process.